Hi, I'm Marco Dörner and welcome to this tutorial on texture synthesis. In this video, I'm going to show you how to write a texture generator with Python and within Cinema4D that will extend an existing texture from the center outward. However, Cinema4D will only be used more like a compiler. In this one, it's all about the logic of the algorithm. So for the first couple of minutes, I'm going to prepare the scene, write the functions, and then I'm going to explain how the algorithm works. If you want to jump ahead, you can find the timestamp in the description. As usual, I start by adding some user data to a null object that will control my script, and importing this then into Python. So there are two file paths and three integers. The first path is set to the source file that we want to extend outward. And the second path is where we want to save our results to. You'll have to write this in manually though, as Cinema doesn't let you choose a directory without a file. Also, you need to import the Cinema4D bitmaps module and the time package, which we will use to document how long the process took. Finally, I also added a Boolean button to control when the script starts. Okay, so we could keep our input picture in the Cinema4D bitmap data format, but this would be very slow to work with. Instead, I chose to read the image pixel by pixel and put that data into a one-dimensional array. However, the bitmap function from Cinema4D requires two inputs to get the data of a certain pixel, the x and y coordinate. My one-dimensional array only has one input, a unique ID. Also, some parts of my code work better with only one number instead of two. So the first two functions I'm going to write are simply translators from one format to the other. If we look at an image, we can associate an x and y value to each pixel. But if we wanted to, we could also number each pixel with a unique number. To convert an ID to an x and y coordinate then, we have to divide the ID by the side length of the image. The result without decimals will be the y, the remainder will be the x. On the other side, we get the ID by multiplying the y coordinate with the side length and adding x to it. So these are the two functions I wrote. The first takes the x and y position and returns an ID. The second takes an ID and returns the x and y position. Next, I'll write a function that loads an image and translates that into a one-dimensional array. So first, we create an empty array and also initialize a new bitmap with the image path. We're going to need the side length of the image. So the function getSize returns a tuple of data, the width and height, and here I then only use the width. A for loop then cycles over each cell in the image and reads the data into the image array with the help of the getPixel function. But this requires an x and y value. So I'll make use of our translator function to convert the ID from the for loop into an x and y position. At the end, we return the image array and the size. That's the array from image function done. But we're also going to need the inverse, so a function that takes an array and returns a bitmap. So here the side length is calculated as the square root of the length of the array by using the power function with a value of 0.5. That means both of our functions assume the input and output image will be square. We create a bitmap, and this time, instead of a file path, it is initialized with the width and height. In our case, that's the same. Then again, we cycle over each cell with a for loop, but now we use the setPixel function, which, in addition to x and y, which we again get from the ID2Position function, setPixel also requires an RGB value, which is the data that will be stored in the cell of an image array. So to recap, we wrote two functions. One that loads an image from a path and creates a one-dimensional array from this, and another that takes an array and fills a Cinema4D bitmap pixel by pixel with that data. So now let's test it. In the main code, we run the arrayFromImage function with the path that was set in the user data, which will return an image array and the side length of that image. The second function, imageFromArray, is given the seed image array as a parameter. And the returned bitmap we store in outImage. And finally, we can use the save function of the bitmaps module to write the image to the path out from the user data plus the file name of that image. Careful here, as \r is an escape character for Python that has a special meaning. So to tell Python it should just read a string as a text without special characters, we need to put an R for raw before the quotes. There is a small typo. Yeah, bitamp should of course be bitmap. And now it works. And there is the seed image. The next step is to write a function that creates a new image with the side length outsize that has the source image at the center. I call this function initializeCanvas, and it gets 4 parameters: the original image and its size, the outsize, and padding, which is the distance between the border of the two images, so the difference between the two sizes divided by 2. This variable gets created after we get the size of the seed image from the arrayFromImage function. And then we can use it with the other parameters on the initializeCanvas function. There, I first create an array with the length outImageSize squared. So this will create a square image. And I'm going to fill each cell for now with the impossible color -1, -1, -1 for red, green, and blue to indicate that the cell is still empty. SID is the ID of a cell in the source image. And once again, with the for loop, I cycle over every cell of the outImage array to find out if a cell should show the seed image or be left blank. So I first check if the pixel ID is in the padding below or above the source image. And if it is, I don't do anything. So in these areas. If it isn't, then I check if the pixel ID is in the padding to the left or to the right of the source image. So in these bits. And if again it isn't, then it must be a pixel where I want to draw the source image. So then, at this cell of the outImage array, I put the current SID pixel of the seed image and I increase SID by 1. So the first time we reach this region, SID will be set to 0. I read this pixel and set it to 1, and so on. That concludes the canvas function. Now let's look again at the video. Here we see the texture growing from the center outward, one ring at a time. So for the final preparation step, I wrote a function that returns a list of all IDs belonging to that ring. The approach is similar as in the canvas function. A for loop cycles over all IDs of the out image, and if we find that the current ID belongs to the ring, it is added to the ring ID list. So we check first if the Y position of an ID is in a column of the ring, up or down, and if it is, we check the X position, if it is the same as a row of a ring. And if not, We try also the other way around. If we find a valid ID, it is added to the list. Otherwise, nothing happens. In the main code, with another for loop, we create as many rings as according to the value padding. And then we color every pixel that the getRingIDs function returns with a value for red, green, and blue. For demonstration now, let's give these rings some funky colors. So red, green, and blue get set to slightly different values depending on the shared variable ring. Seed image array also should be out image array now. And I also modify the string to create a different file name for each ring. And the second variable gets filled with 0s to 3 digits to keep the same format for all frame numbers. And as these two lines should be called for each ring, we need to include them into the for loop. Okay, let's test this. I forgot to add the extension PNG to the file path. Yes. And when we try this again, there are the ring images. Now let's look at how the texture synthesis algorithm works. The concept is simple. Around each blank pixel, the colors are sampled to create a small image patch with the current pixel in the center. Some of the neighbors might be blank, but with the fingerprint of the available colors, the algorithm searches the entire picture for a similar patch. So for every pixel of the image, it creates a second patch and compares the colors at the same position with the original. From a best match, the color at the center is used to fill the original pixel. So for us, this means we need two things. One function to create the patches, and a kind of catalog of these to search the best match efficiently. These are the two functions that I wrote. Sample patch takes an image array, the ID of the current pixel, and the side length of a patch. With two for loops for the x and y offset, it cycles over all neighbors around the original pixel, depending on the size of the patch. And if the neighbor is not out of bounds, and if the color of the neighbor is a valid color, I increase the counter. The color of the neighbor, valid or invalid, gets added to an array. At the end, both the array and the number of valid neighbors is returned. Secondly, there is the catalog of patches. So the generateLOT function cycles through all pixels of an image array and calls the sample patch function for each one. If the returned number of valid neighbors matches the square of the patch size, meaning if no neighbor color is invalid, then it adds the patch to the reference LOT. Unfortunately, we can't really show anything of this yet, as it doesn't make sense to write the whole reference LOT into a picture, or pictures. But what we can do is create a LOT from the seed image and then print its length. (3,844 entries. The seed image has a dimension of 64 by 64, but because for the reference LOT we only consider full patches without any invalid neighbors, we lose some rows and columns on each side. In the case of a patch size of 3, one at the top, bottom, left and right. So we should get entries for each of the remaining 62 by 62 pixels. 3,844. Finally, we need a way of comparing two patches and measuring how similar they are. Here, the for loop cycles through each cell of both patches simultaneously and, if their color is valid, calculates the difference between the RGB values. So the lower the deviation, the closer the match. The result can also be negative though. So because in the end all deltas are added together, it is necessary to either take the absolute or use a power function like I did. In fact, I treat delta R, G, and B like vectors, and my final score will be the length of that deviation vector. Now everything is prepared, and we can start writing the logic of the algorithm. A word of warning though, the process can be very, very slow. To speed it up, I used a module called Parallel Python for multithreading, as the capabilities of vanilla Python seem to be rather poor in that regard. Installing this module for Cinema4D seems possible, but would exceed the scope of this tutorial. Still, the way I present the code here will reflect how to write with multithreading in mind. This means that parts of the code can work isolated without modifying or reading shared variables. So, because of that, I write a new function, job, that, with the arguments given, is fully self-contained. The variable min_valid_neighbors serves as a quality control. Obviously, we need to find at least one valid neighbor, but one alone would be very inaccurate. A too high requirement might not find enough results though. For now, I leave it at that, but I'll explain later how I came up with this formula. With best score, the idea is that the lower the score, the better the match. So the starting value has to be very high. Next, to get the patch of the current pixel and its neighbors, I call the sample patch function, which arguments I can look up on top. And if there are not enough neighbors, I terminate the function immediately. Otherwise, we now run through all patches stored in the reference slot and compare each with the current patch. So, if the average score per valid neighbor is smaller than the previous best score, this becomes our best pixel so far. So we save the score as best score and the color of the center pixel of the patch, which we get with this formula. In the end, we return the best color we found. In the main function, let's get rid of these bits. And inside the ring loop, for each ID of the ring, we call the job function with this ID. The results are added to a new list. This might seem a bit strange, as we could color the pixel right away, but remember that in case of multitasking, we cannot affect any variables that are being used. In this case, for instance, the outImage array. So, with another loop over all the results, we check if the color is valid, and if yes, the pixel is filled with the newly found color. Done. Let's run this. Valid neighbor has one too many eyes. After waiting for a while, we got a result. But there are a couple of problems with it. First, as expected, it's very slow. To get a better idea of what's happening, I'm going to add timestamps to the output. To get the time passed, I subtract from the current time the time at the start and convert that difference to minutes and seconds. So, after each ring is done, this will print the time the algorithm took to this point. Secondly, for this image, a patch size of 3 seems to be too small. As soon as we choose a different patch size, the result should be more accurate. I went with 5 here, but if you have the CPU power, you can try 7 as well. After waiting for about 5 minutes, the results are in. They are clearer, but now let's talk about their strange shape. We can see that new pixels are only generated in the middle sections and none around the corners. This is because of the way we wrote the job function. If a pixel doesn't have enough valid neighbors, the color will be left at -1, -1, -1. There are two ways to solve this problem. First, we could just set min-valid neighbors to 1. I don't like this approach though, as it will create less accurate solutions around the corners, exactly in those areas that are left white in the first result. You can increase the patch size for better accuracy, but that will slow down the algorithm significantly. Instead, I thought, what is the greatest possible number of neighbors any pixel has at least? So this pixel has 3 neighbors. This one has 2 and this one only has 1. But if all other pixels of the same ring were solved already, it could have 3 as well. So what I found was that without starting a new ring, the maximum number of neighbors a pixel has at least is under this area of the patch. And that is exactly what my formula does, in fact. This doesn't work with a single multi-threading approach though. As I said, we cannot access data that is being written by other tasks, in this case the color of the neighbor pixels. But we can start another multitasking block or run the first one again to go over all unsolved pixels before we start the next ring. So here are some small adjustments to the main function. First, we write all IDs of the ring into the to-do list that we created. And together with the while loop, the idea is that once this to-do list is empty, all pixels of the ring are filled. For while loops, I also always like to add a secondary safety variable just in case I made an error with the first condition somewhere. The multi-threading job now is initiated with the IDs from the to-do list. On the first iteration, that will be the whole ring, like before. At the end, after we've gone over each point on the to-do list once, we can empty it and fill it up again with only the unsolved pixels now. So again, let's give this a try. And while this is calculating, I'm going to get a coffee. See you in a bit. And after a couple of minutes, here are the results. This is looking already much better. I did a comparison of 3 options. The first has min-valid neighbors set to 1 and a patch size of 5. As we see, there is a lot of error or garbage pixels. In the center, there is my approach. The time is practically identical, but the result around the corner is much better. On the right, min-valid neighbors is again locked at 1, but patch size is increased to 7. This gives the best result, but also comes with a big drop in render time. Looking at the image sequence, we still see a lot of garbage pixels. To improve the result, you can try playing with the patch size or modifying the seed image, but chances are there will always be some errors. So instead, the last thing that we do, we can give each pixel another chance. On the first iteration, each pixel only has a couple of neighbors, but we can run the algorithm again after the whole picture is solved and use the full patch to detect the best matching color. All we have to do is to add another loop using max iterations as limit. Let's also change the file name from using ring to a variable frame to get a continuous numbering of frames. That's it. Credit for this algorithm goes to this paper by Alexei A. Efros and Thomas K. Leong. However, I made some modifications. For one, their paper doesn't propose multiple iterations over already solved pixels. Also, they are measuring the distance between a pixel that is being filled and the reference patch and weigh the results accordingly, so that, for example, closer patches will be preferred to others that are farther away. This makes sense for images that have different parts, but as for seed images that are very uniform, it's not necessary. Thanks for watching. Also visit my other tutorials and my website on phantom.de. Cheers!